We will now consider triple integrals over more complicated regions. For example, we're going to compute by triple integration the volume of the region T that is bounded by the parabolic cylinder x equals y squared and the planes z equals 0 and x plus z equals 1. So let's begin by figuring out what is the region T. I'm going to start with the parabolic cylinder x equals y squared. In the xy plane, that's just a parabola. So it's going to look something like this. And then we're imagining that that parabola is being extended up and down in the z direction. So they call it a parabolic cylinder because you can think about, for a circle, if you extend that circle up and down, then that creates a cylinder. And so in that same way, we're going to extend this parabola up and down in the z direction, and that's what forms what we call a parabolic cylinder. And then we're going to look between the planes z equals 0, so that's the xy plane, and then x plus z equals 1. Another way we can write x plus z equals 1 is z equals 1 minus x. So if I plot the line z equals 1 minus x, then I can extend that in the y direction, and I can get a sense of what this plane looks like by extending it in both the positive and the negative y direction. And so now what I'd like to do is find the volume that's underneath that purple plane but stays within the blue parabolic cylinder. So we can find volume by integrating the function 1 dv. So we're going to integrate the function 1 dv. That will get us the volume. The question is what are the limits of integration here? Well, I'm going to write this down first as an integral dz. I want to find the volume that's underneath that purple plane. So I'm going to integrate from z equals 0 to z equals 1 minus x. Then I'd like to describe the region with the parabolic cylinder. Okay, so that region is going to go from x equals y squared out to where the plane hits the xy plane. Okay, so I'm going to integrate from x equals y squared out to x equals 1, because at x equals 1, that's where z is equal to 0. That's where we've hit the xy plane. So I'm going to integrate that dx. And then finally, I would like to integrate over the relevant y's. So if we're going to let x run from y squared out to 1, then y squared can be as much as 1. Y therefore goes between minus 1 and 1. So let's just look at why that's true by taking a quick sketch of the xy plane here. So here I'm going to draw x equals y squared. That's going to look like this. And then what I'm going to say is I want to integrate over that region. So this region right here. Okay, that starts at x equals y squared. But then notice that that means that y is between minus 1 and 1. So x goes from y squared to x equals 1. Y is between minus 1 and 1. Sometimes when you're doing these triple integrals, it helps not just to sketch something in 3 dimensions, but also sketch what the xy region might be in 2 dimensions. Now what's left is just to compute this triple integral. So we're going to integrate the function 1 dz. So that's going to give us just the integral from minus 1 to 1. So this is y equals minus 1 to y equals 1. And then we have the integral from y squared to 1. And then if we integrate 1, we're going to get z evaluated between 0 and 1 minus x. And that is what we want to integrate then dx dy. So this becomes, let's see, the integral from minus 1 to 1, the integral from y squared to 1 of 1 minus x, and then we're going to integrate that dx dy. So that leaves us with the integral from minus 1 to 1. I'm going to do the inner integral of 1 minus x. So that's going to give me x minus 1/2 x squared. I'm going to evaluate that between y squared and 1. And then when I'm done with that, I'm going to want to integrate that dy. So this is the integral from minus 1 to 1. I'm going to now substitute in my limits. So x is 1 minus 1/2 1 squared. So 1 minus 1/2. And then I'm going to subtract. I'm going to substitute in x equals y squared. So I'm going to get a y squared minus 1/2 y to the 4th. And all of that is then going to get integrated dy. Okay, so this, I just want to simplify real quick. It's the integral from minus 1 to 1. 1 minus 1/2 is going to be 1/2. And then I'm going to have a minus y squared, and then a plus 1/2 y to the 4th. All of that I'm going to integrate dy. I'm going to notice that that is an even function, and so there's a symmetry there, so I can actually do twice the integral from 0 to 1. So I'm going to multiply everything by 2, so I'm going to get 1 minus 2y squared plus y to the 4th. And I'm going to integrate that from 0 to 1 dy. Finding the antiderivative, I'm going to get y minus 2/3 y cubed plus 1/5 y to the 5th. I'm going to evaluate that between 0 and 1. So I'm going to get 1 minus 2/3 plus 1/5. And that, finding common denominators, is going to be 8/15. So the volume that's underneath that purple plane but stays within the parabolic cylinder is going to be 8/15.